So, do you believe that whatever probability that we computed here is realistic?
Yes.
No, yes, maybe, no, absolutely not, especially in Florida. So the probabilities here, I'm assuming that they are equally likely, right?
Yeah.
In the sense that 1/3, 1/3, 1/3, that's a mistake, not going to happen. Two, what if there is a storm, right? Day 2 will depend on day 1, correct? Depending on the path. So this particular problem makes an assumption that the probabilities are equally likely and that the days are independent of each other. But there are cases where events can not be independent in the sense they could be dependent. And that's where the multiplication rule comes into play. Let's say A and B are 2 events. The multiplication rule pretty much is an extension of the fundamental rule of counting. We're just moving from the number of ways to probability. That's all. So suppose I have A and B to be 2 events, and I make a condition that B depends on A. So the probability of A and B happening together will then be given by probability of A multiplied by the probability of B vertical dash A. Patience, it's coming. So B vertical dash A probability. The probability of A and B is equal to probability of A multiplied by the probability of B vertical dash A. Now, vertical dash does not mean you are dividing, doesn't mean anything other than simply suggesting that this is the probability of B given that A had already occurred, or the probability of B given or conditioned on the event A. Good. At the end of the day, this is going to be a number, that is going to be a number, specifically probabilities, and you're going to multiply them. Good. No division, this is not division. It simply means the conditional probability of B given A. If I turn around and said, if A depends on B, how would that expression change?
Then you are the probability of B times probability of A versus us. PR of B times PR of A.
A and is the same as A intersect.
Oh, yeah.
And probability of A given B is not equal to probability of B given A. What would happen if A and B had nothing to do with each other? How would you rewrite this?
Pure rate and pure.
Sorry?
Wouldn't it just be the probability of A times the probability of B?
It would be. So if A and B are independent, A has got nothing to do with B, likewise B has nothing to do with A. So we'll just have probability of A multiplied by probability of B. In practice, this is related to the concept of replacement and with replacement, without replacement. The book does get into some counting rules, so it's good to know what with replacement and without replacement means. So let's just say I have a basket full of candy, and let's say I have 9 Butterfinger bars, 9 Almond Joys, and 4 Snickers. Good. So in total, how many do I have? 22. So what I'm going to do is I'm going to close my eyes and randomly pick one, assuming that I can't tell the difference between any of the candies that I have. Good. They have to be identical. What is the probability that I get Butterfinger? 9 over 22. So I can simply write this as probability of getting Butterfinger. Yes. Next step. I love candy, so done with that candy bar, wanted more. So I close my eyes, stick my hand inside the box, grab one. What is the probability that I would get an Almond Joy?
9 over
9
20.
over
What?
22.
9 over 21. What is that?
You already ate one. Because you already took one candy out of 9.
Because I already took one candy out of the box and I ate it. So whatever probability that I compute for this particular event depends on the previous event. So that would simply become a conditional probability, and I can write it as the probability that I pick Almond Joy given Butterfinger. Does that make sense? If you rewrote it A, B, A, so if this is A, that would be B, and that would be A. So I can keep on writing it in sequence, but that would be a lot. We don't want to do that. Let's say, same scenario. So this is without replacement. I kept eating. Suppose I have diabetes. I grab a candy bar. I really want the candy bar, but I can't have it. So I grab it, feel the candy bar, and put it back and forth. That's
So sad.
so very sad. So what is the probability that I will get Butterfinger the first time? 9 out of 22. But I didn't eat it. I just felt it, put it back. I get the urge again, so I put my hand inside the box, try and grab one. What is the probability that I would pick Almond Joy?
9 out of 22.
9 out of 22. Doesn't change. So in this case, the experiment is done without replacement. When I first started, we had the sunny, cloudy, rainy example. Is that problem done with replacement or without replacement?
Where?
without.
Wait.
With, it's done with replacement. The reason being, every single day is independent of the other day. That's one. Two, each day has sunny, cloudy, rainy, right? And when I started this entire multiplication rule, I mentioned that it is not realistic for us to assume that the days are independent of each other. So anytime you have with replacement, naturally you would have independence. If things are done without replacement, then you will end up getting dependent events. Good, are we clear? With replacement, without replacement, and independent and dependent events. We are not dividing stuff here. I can't stress that enough. This simply means the conditional probability of the event A, given that the event B had already occurred. Good? Clear? Okay. Okay, so currently the table shows whether workers contribute or they do not contribute to retirement at their work. And clearly this is a dependent case because, yes,
Your table is wrong. 207.
It's
should be
143.
what?
207.
It's 143 and 107. It's
Yeah.
143.
Bad math. So clearly we want to determine if gender plays a role in terms of contributing to your retirement. A table of this sort is called a two-way table or a contingency table. What does contingency mean? Catch.
Here's the catch.
Okay,
Is that wrong? I don't know how to say it.
that's, yeah, but
Hey Siri.
another way.
Given this,
Given that you are conditioning on something, hence the name contingency. You are placing a condition, that's the catch that Annabelle was talking about. So we want to find the probability that a randomly selected worker contributes to retirement savings, given that the worker is male. So I am going to call event A to be male. Event B to be contributes to retirement savings. And we want to find the conditional probability of B given A. You contribute to retirement given that you are a male. So we sort of have to rewrite the multiplication rule to solve for probability of B given A. So if I want to solve for probability of B given A, what would I do?
divided by
Divide by what? Just A or the probability of A? Probability of A on both sides. The numerator is the joint probability of A and B together, denominator is the marginal probability. And I'll tell you why we call it marginal probability, because it's quite ingenious. Is it? So when I say probability of A, I'm looking at just the probability of someone being a male. Do you agree? So look at that table and tell me what is the probability that someone is a male? 1/2. How did we get that? 250 divided by 500. Yes. So probability of A is 1/2. We got it by dividing 250 by 500. This is a table, and the total is at the margin, hence the name, marginal probability.
Whoa.
Mind blown. So denominator is 1/2. Now we've got to find the numerator. A and B happening together. So the probability that you are a male and you contribute to retirement savings.
116 over 250.
116 over,
250. No,
is it 116 over 250 or is it 116 over 500?
should it be 500 because that's the total amount of people?
Why not 250?
That's just.
Because that's just considering males.
Exactly. So 116 divided by the total number of people, male, female, doesn't matter. If I just looked at 250, I am conditioning on just males, right? So
Good question. Instead of doing all that, can you just do 116 over 250? That's it.
could you be patient? Because we're about to go there.
No.
So, so 116 over 500 times 2 over 1, which gives me 116 over 250. And Alex is absolutely right. Instead of doing all this, we could have gotten the answer directly from the table. Yes? If I'm conditioning on males, I'm focusing on the total pertains to males, and that would be 250. Out of those 250, how many of them contributed to retirement savings? 116. So it is 116 divided by 250. Yes.
Okay, no.
The reason why I did it this way is because you've got to understand the multiplication rule, because there are other problems where you may not be able to get to the probability answer right away.
Drop this fast, don't give us that. This contingency table, right? Just double check that.
So of course I could do it the easy way, but I want you guys to understand the rule. So what are we trying to find? We are trying to find the probability that someone is a female, given that they contributed to retirement. So instead of AB, I'm using CD, but this always means probability of C intersect D divided by probability of D. Easier way to remember, numerator is always this and that. The denominator is always the probability of the event that is on the right of that vertical dash. So what is the probability that we have someone who's female and contributes to retirement? 143
over 500.
What is, thank you, over 500? Yeah. What is the probability that someone contributes to retirement? 259 over 500. flip and multiply, you would get 143 over 259. But we didn't have to do all that. As far as a contingency table is concerned, if I'm conditioning on the fact that someone contributed to retirement savings, I am conditioning on this column. So I'm going to focus on that total and look for female. So it would be 143 divided by 259. So with contingency tables, it's easier to do conditional probabilities, but do understand the multiplication. Good.